Let me begin with a word of prayer. Heavenly Father, we thank you for this time we have together, and I just pray that you'd help us to gain new insight into our problem, Lord. In your name I pray. Amen. All right, so I want a quick run through something I've just worked out, and I think this is partly I think you invented this, Cooper, or at least you encouraged me to think about it. So if we took a point in here, we have something like rho e to the j phi, where that's equal to x plus jy, and so rho is the, what is it? Square root? Is square root of x squared minus y squared, is that right? Oh, absolute value. There, I don't guess I need it. Oh, but you're right. I should just go ahead and you're looking ahead. Good idea. So any point in this first sector, in sector 1 looks like that. Any point in here looks like j rho e to the j phi. Anything over here has the form minus rho e to the j phi. Anything down here has the form minus rho j e to the j phi. So basically, an arbitrary hyperbolic number can be represented in sort of, I don't know what you want to call this thing, sort of pseudo-polar form or something. Well, let's say minus 1 to the s, j to the, I need some letters here. Let's say a, b, e to the j phi, you know? And so if you look at, for example, z bar is equal to x minus jy by definition, and it's also equal to, you know, minus, well, the point here is, let's see here, I gotta be careful. Oh, I forgot a very important thing up here, right? Rho. Kind of burying in the lead there. But I think we can argue that z bar is really what? Minus 1 to the a, minus j to the b, e to the minus j phi. Rho. See, rho is really the square root of z bar absolute value. So when you conjugate that, rho is fixed under hyperbolic conjugation. So, I mean, notice if we let w equal z to the m, right, then, and if z bar is equal to c, so z bar equal to c is what? What's that? Rho squared. Yeah. Well, I guess it's the, as I've set things up here, it's the absolute value of x squared minus y squared. But this is actually just straight up x squared minus y squared equals to c, right? So depending on whether c is positive or negative, in which sector you're in, that's a hyperbola, opens left or right or up or down. But we can also consider this map, right? Z maps to w equals to z to the m, right? And if you think about the image of the c hyperbola, if you'll let me call this the c hyperbola, right? Or we could call it the c hyperbola, but we shouldn't do that because it's nonsense. All right, c hyperbola, even c hyperbola is questionable. Anyway, the hyperbola indexed by c. Then what do you got in the w plane? if you calculate W bar, what do we got? We got ourselves a minus 1 to the A, minus J to the B, E, E to the J phi, right? Rho, that to the M power times minus 1 to the A, minus, oh, did I say minus? I meant J. Sorry. Over here, minus J to the B, E to the minus J phi, rho, to the M conjugate. Right? I'm assuming W is equal to Z to the M. And what do we get? Oh, I'm sorry, I already did the, there's no bar here, right? I already did it. So sorry. So, I mean, we've got, minus 1 to the A, minus 1 to the AM, minus 1 to the AM, J to the BM, minus J to the BM, E to the JM phi, rho to the M, E to the minus MJ phi, rho to the M. I know these laws of exponents for hyperbolic exponential. If I take hyperbolic exponential to the M power, it is M times the argument of the hyperbolic exponential. There's sort of a hyperbolic analog of de Moivre's theorem, to say it stupidly. But these are natural enemies, of course. Right? And how about these? Again, well, this one is just automatically 1, right? Because that's minus 1 times minus 1 to the AM, which is 1 to the AM, which is 1. And this one here is actually what? This is minus J squared to the BM, right? But J squared is 1, right? So this is actually minus 1 to the BM, right? And how about ZZ bar? That was rho minus 1 to the A, J to the B, right? E to the J phi, rho, times rho minus 1 to the A, minus J to the B, E to the minus J phi, rho, right? Oh, sorry, I got my rho already. Can't figure out where to put my rho's. Anyway, the point is you got rho squared, right? Minus 1 to the A's, they'd be canceling. The hyperbolic exponentials, these guys are natural enemies. They're gone. What are you left with? J times minus J to the B, which is also known as rho squared to the what? But that's also equal to what? That's equal to C, right, by construction? This up here, we could also look at, of course, as rho squared times minus 1 to the B, all to the M power, right? Right, which is C to the M. So what's this show? I mean, I think if you take a step back and think about this in terms of zero divisors, it's kind of totally unsurprising. Because when you think about the monomial, like w equals z to the m, what are you doing? You're taking a hyperbolic number, raising it to the mth power, right? So if you put in zero divisors and you take multiples of zero divisors, what do you get out? Product of zero divisors are zero divisors. So it stands to reason the monomial map has to fix the zero divisors, the spans of 1 plus or minus j. So, I mean, that doesn't prove that it maps hyperbolas to hyperbolas, but it's kind of not that surprising. Now, it's not the same. The hyperbolas are not fixed, right? And in some sense, they're kind of disoriented. If you use phi as a parameter on the hyperbolas, you'll notice that under the map, well, when I actually worked out the details, and I'm a little bit, well, so this is what I got. So for I used h instead of rho. Let's see here. H, J rho minus H, J rho. Yeah. So, see guys, this is what I see is, if I start with these two hyperbolas over here, these ones kind of, they all flow. The initial ones kind of flow towards the that direction, or these ones kind of flow up in that direction. The mapped ones, they have, oh, I'm sorry, this is actually for the reciprocal. This is for the -1 power, I think, if I remember right. Yeah, I did for m equals -1. I think that's what I'm looking at here. It must be right. Something like that. But the reciprocal, like instead of if you use the phi to parameterize the hyperbola, then I think that the image under the reciprocal map, they're not oriented the same way. They actually flow opposite directions in that sense. So if you keep track of the orientation of the curves, the reciprocal map will like disorient them in some sense. But hyperbolas map to hyperbolas under a power map. Now, on the other hand, I thought, well, what about other functions? Like, what about, sine, cosine, exponential, log? What happens to hyperbolas under these? So my new insight for this weekend was that I should look at it as ZZ bar. So to test whether or not the image is a hyperbola, I got to check, for example, is cosine of z times cosine of z bar equal to a constant, given that ZZ bar is a constant? That was what I would need for the image to be a hyperbola, and it's not hard to see. Like if you look at e to the z times e to the z bar, you get e to the z plus z bar. If you take cosine z times cosine z bar, you get a sum of sines of plus or minus z bar divided by 2 by the product of some identity. So I don't think for my initial thought is sine, cosine, exponential, log. Nothing particularly nice happens to hyperbolas when you feed it. You don't get hyperbolas back out. You get disgusting whatever, yeah. So that's the one thing I found. Now, the other thing I want to share with you guys, and I'm sorry, this has nothing to do with modern Rosa directly, but I'm kind of excited about this because it's something I was trying to do with you. And so what I'm going to do is I'm going to start at the end of it rather than the start. I'm not going to show you how I derived it. I'm going to write it down, and we are going to calculate the component functions of this. But before I do that, let me just give you a little. Now, some of you have had differential equations, some of you haven't, right? You all have had differential equations. Hooray! Oh, yeah? That's funny. Did you? Let's see here. So, I'm showing you episodes 4, 5, and 6 before. Yeah, I should have numbered these papers. This is going to get me into trouble. All right, where's that thing? So I got to share this with you guys. Then we'll get back to the pesky task of trying to lay special relativity over the hyperbolic numbers, or at least say something about it, a la the Mater and Rosa paper. Okay, so here it is. Essentially the wave equation, right? Unit speed anyway, would be UTT equal to UXX. My thought is that if I can work this stuff out for unit speed, it's not a big deal to go back and then to add speed and to clutter things. So just set the speed equal to 1 to start with when we're fleshing things out. And also, I'm going to set the, the interval we're trying to solve the wave equation equal to 1. So let's try to solve this subject to the boundary conditions that, u of 0t and u of 1t equal to 0. So the fixed endpoint conditions for the wave equation. All right? You guys know the usual song and dance. We propose a product solution, right? Typical solution technique, you say, well, u of xt should be something like x of x times t of t, right? Plug it in, we get t prime prime times x equals to x prime prime times t. Separate variables, we get x prime prime over x equals to t prime prime over t. Set that thing equals to, say, minus j. And then we face two ODEs to solve. X prime prime plus jx equals to 0, and t prime prime plus jt equal to 0. By the way, we can't have this room officially. There's something that happens in here eventually. So at some point, we're going to get interrupted. I know, but there's like some kind of something that happens in here at some point. But we have another room officially, so we'll just go to that room when that happens. Yeah. Anyway, so, all right. You go through the usual song and dance. These these imply, when you feed it to this, that you need x of 0 is 0, you need x of 1 is 0. Those are the boundary conditions. So those boundary conditions put on the first ODE, they force j to be n squared. So these force j equals to n squared, and so you actually have x prime prime plus n squared x equals to 0, and likewise t prime prime plus n squared t equals to 0 by the usual arguments in the very end of DEs where we study basic PDEs. And so the fundamental product solution is something like xn of x would be something like sine of nx. If you look at that, that's going to work, right? I think I was being too careless to be lazier. Pi. That's the truly lazy boundary condition, right? Because then when you plug in x equal to pi, you get n pi for any choice of n. And then over here, of course, we get Tn of t. It's either going to be, either you can get a cosine nt or you get a sine nt, right? And then typical thing is to use Fourier magic. And I say Fourier magic because we don't do the analysis. That means it's just magic. And we construct it as a formal sum, right? Say a sub n sine nx, maybe cosine nt plus b sub n sine nx sine nt, right? And this is what I call this the blank template solution in my current teaching. You pick coefficients a sub n and b sub n to fit a given initial condition for the wave equation. That's how we do it, right? All right. Oh, by the way, Cooper, I have no idea what to do with this. I just thought it was interesting. Yes. Oh, you guys have with, yeah. All right. Well, it's in the syllabus. You know, this is the thing that kind of irks me is I'm starting to have an undercurrent of students saying I didn't follow the syllabus. Excuse me, I did follow the syllabus in differential equations. I cover what the syllabus says. I know, I wrote it.
Did you put additional topics?
No, it has PDEs in the syllabus. The fact that it's sometimes not covered in other sections doesn't mean it's not part of the syllabus. It means the opposite about the other person. But of course, we would never complain about too little being covered. We would only complain about the actual amount being covered, because I don't know why I work so hard. I should just, you know, honestly, guys, at some point or another, I'm going to learn to stop trying to teach hard things. So it's really not a comment for you guys. You're here after all. Yes, I know. It's true. Yes, it's just the, yeah, exactly. Your voices are not heard as loudly, unfortunately. Oh, okay, so I found something. See if I can find it again. So Cooper already knows the punchline. Maybe, if you checked his email. Wow. Oh. All right, come on. Where'd you go? If this doesn't work out, I'm going to be annoyed. It took me a long time to find this thing. Here's function. Function fn of z equal to sine of n divided by 2, 1 plus j times z, plus the sine of n divided by 2, 1 minus j times z. Is this a hyperbolic function? I mean, is it hyperbolic differentiable? We know that if it is, its component functions are solutions to the underlying wave equation, right? So I want to suggest in this lecture we're going to use z is equal to x plus tj. All right, so we're basically just setting y equal to t. So one form of the hyperbolic Cauchy-Riemann equations was what? Partial f partial z bar is 0. The chain rule works. Like if you differentiate this with respect to z bar, you get cosine of that stuff times the partial derivative of this with respect to z bar. Cosine of this stuff times the partial derivative of that with respect to z bar. The stuff in the front's a constant. It pulls outside of the partial differentiation with respect to z bar. And by my construction, and even the other author's construction, partial z bar is 0. So yes, it is elementary calculus to show that partial fn, partial z bar, is equal to 0. Therefore, fn from the hyperbolics to the hyperbolics is h differentiable. In fact, everywhere. So what are its component functions? Let's calculate. Fn of z equals to, u, and let's drop the n. Let's calculate u, u plus jv, where u and v are real valued. How should we do that? Guys have any ideas? I'll pick on the first half of it. How about that? I mean, there's various ways of doing this. We could look up the product to sum identities would be one way. Maybe that's the best way. And there's another way I see right now. I'm going to try it that way. That's really n over 2 z, right, plus nj over 2 z, right? But I don't even like that. I mean, well, I don't know. I haven't done this way of the calculation yet. I'm not sure what the best. You guys, what do you think that? I mean, we can do this. Let's try it and see where it takes us. Take me a second. This is cosine nz over 2. Sine. I mean, Daniel proved this in his paper, that you have the usual laws of adding angles law for sine. So it goes cosine sine plus, sine cosine if the arguments stay the same. Now, I can simplify that further, although I'm not sure it's wise, but I can. I mean, this is kind of a neat calculation to share with you guys anyway. J, if you think about it, pulls out a sine. And in contrast, cosine absorbs J. The reason for that is that the power series expansion for J involves even powers. So when you square a multiple of J, you end up with a J squared, which is just 1. In contrast, the sine is based on blah, basically think about theta J to the 2n plus 1. What happens there? I mean, I should use something other than k, 2k plus 1. I mean, that's J to the 2k plus 1. Theta to the 2k plus 1, which is just j theta to the 2k plus 1. I mean, so when you do that order by order, you get a j everywhere, and the theta argument remains. So long story short, you can pull the j out. And likewise, the j gets absorbed there. Oh, is it the same thing? Oh. 1 plus j times what? Cosine blah, sine blah?
But then, wouldn't it be wise to just take it back to, put those together?
Hey, wait a second.
No, sorry. But well, yeah, couldn't we just
Right.
go backwards?
Go backwards.
What's the trigger?
Yes, thank you. So we know that sine 2 theta, right? Or rather is 2 sine theta cosine theta, right? That's actually something that's true for sines over any algebra, in particular hyperbolic. So that gives me, I need a half, right? So 1/2 1 plus j sine of nz. So let's call this thing 1. Let's call this thing 2. So this is equivalent to 1, and I think it's better. Let's go through the same calculation for 2. What do we get for 2? So we've got nz over 2 minus njz over 2, right? Which gives us the sine of nz over 2, the cosine of njz over 2, minus the cosine of njz over 2, sine of nz over 2, right? I might have butchered that. Just give me a second here. That's supposed to be nz, yeah. I should keep the arguments the same if I'm going to flip the sine and the cosine, right? So I can't make up my mind what I'm doing. Anyway, there I did it. Okay, so absorb the j. Pull it out of the other one, right? Write them in the same order to make it manifestly obvious what we're going to do. So that's 1 minus j, right? Kind of the same. Not quite, though. Oh, that. But there's an important distinction between these. One plus j, 1 minus j. So what did we just figure out? We figured out my f of z is actually the same as what? Oh, what is it? It's 1 plus j over 2. Oh, that's funny. That's funny. 1 plus j over 2 nz. Oh, man. That is really something. So apparently, Cooper, you can improve on my formula. Because what did you say happens when I add these? The j's cancel, we're just left with what? Sine of nz. Okay, what are the component functions of that? N times what? Times x plus jt, right? Which is what? This is sine of nx plus njt, which is what? Sine of nx cosine of nt. Well, I'm sorry, I'll do in between step here. Cosine of njt, right? Plus the cosine of nx, the sine of njt. But again, my pull out the j or absorb the j trick, identity, whatever you want to call it, we got ourselves a sine nx cosine nt plus j times the sine of nx. Oh, I'm sorry. Son of a gun. Cosine nx, eh? Huh. Yeah, that is that's a cosine, right? Yeah, okay, fine. Cosine nx sine nt. So, yeah. This, of course, is one of the standard pieces in the blank template solution. And the other piece is not. Right? At the moment, I don't have that yet. I mean, depending on what kind of boundary conditions you're looking at, right? You either want sines or cosines of x, and you either want, sines or cosines of t. It looks like this has got some kind of admixture of, it's like half of what I want for the usual fixed endpoint problem. What is cosine? I mean, cosine, that other piece is a, what is that even? Did I do this right? That's right. All right, so let me tell you how I actually found this. Right, want to know where this came from? I mean, because it's kind of weird, right? I mean, is it apparent to you that this is sine of NZ? It's not obvious to me at the moment. But the way I found this, all right, guys, was I started with u equal to cosine nt, sine of nx, right? And then what I did was I just solved the Cauchy-Riemann equations. I set ux equal to vt, and I set ut equal to vx. And these, of course, told me that v was equal to sine nt cosine nx. Oh, and that is, in fact, what I just recovered again, isn't it? Right. Sorry, it had slipped my attention that it wasn't, I was hoping that this one function had both this kind of thing and that kind of thing in it. It just doesn't, right? King conjectures that if we use cosine nz, it's got what we need. I want to. Hey, let's try it out. So let's try it out. G of z equal to cosine nz. What's that got in it? So that's the cosine of nx plus njt, right? Which is cosine nx cosine njt minus sine nx sine of njt by the usual adding angles formula for cosine as derived in Daniel's paper. And again, we absorb the j, and so we got ourselves a cosine nx cosine nt minus j sine nx sine nt. That's the missing link over there. That's the squiggly wiggly wiggly. This is quite beautiful. This suggests a hyperbolic Fourier analysis of the following. So maybe we should something like this, f of z equals to the sum n equals 1 to infinity, appropriately chosen hyperbolic constants, a sub n, sine of nz plus b sub n cosine of nz. And if you're willing to throw in a j right here, right here, why not just call it the sum over appropriate hyperbolic constant Cn e to the jnz, in complete analogy with the typical complex Fourier solution with complex coefficients, the real part of which you can peel off as real solutions to the wave equation. So why am I excited about this? Because it's cool? Fine. You don't understand. This, I'm happy about this for the sake of your paper, Cooper, because all you have to write down is consider cosine nz. Consider sine nz. It has these component functions, which are thus, solutions to the wave equation. This is not how I found that. I found it from integrating the Cauchy-Riemann equations and about 2 pages of product sum identity stuff that finally, at the end of another not entirely obvious simplification, got me to the 1-2 step, which then, after I work out with you guys, simplified further, stupidly further, to this, which is kind of embarrassing. Like, why not just try that to start with, right? I mean, if you're going to believe in an analogy to the Fourier analysis existing over the hyperbolics, surely c to the n e to the n jz is a good place to start. But what these calculations show is that at the real component level, these kinds of functions produce what? They produce your favorite sine nx cosine nt and sine nx sine nt. These are the fundamental building blocks for Fourier analysis to build solutions to the wave equation between 0 and pi with fixed endpoints, given any initial reasonable set of initial condition and initial velocity. But you see, now we have a way, right, of packaging any of your favorite initial Fourier expansion that you can study from the end of the usual DE's course, right? We can realize that Fourier solution as the real component of a corresponding hyperbolic function, which then means we can feed it to the hyperbolic conformal map idea and create solutions to the wave equation that I have no earthly idea what they mean. That's what I want to do. Right? Actually, I don't care so much about the infinite series aspect of it. Just picking a, pick your favorite, just sine of z or something would be a good starting point, right? I mean, that's we just figured out that, let's see here. If your initial velocity is 0, right? If your initial velocity, I think. Oh, guys. I know what's confusing me. So very wrong. So when you have a wave on a string, right? Maybe this is your initial shape, sine right? And suppose it's initially just put into a sign and kind of just look. So the initial velocity is 0. What I have is that u of t, well, excuse me, yeah, u of no, oh, I do have it. 0t is equal to, okay, this is fine. I'm sorry. Dang it. I'm sorry, guys. So I also need to be given u of x comma 0 equals to f of x, right? Well, let's say f1 of x and partial, oh, here it is, partial u, partial, this is the thing I'm struggling to make words on at the moment. The initial position and initial velocity have to be given in the standard problem. I mean, there are other sets of well-defined boundary value problems, as is elegantly extended by the Sturm-Liouville discussion, but that's outside where I ever teach in the course. So I guess what I'm trying to get at here is so what would the if my initial if my initial string is plucked like that, what's the solution then? Is it sine x cosine of t? So here, does this give us u of x comma 0 equal to sine x, and also partial u, partial t at any x at time 0 is 0? I think it does, because u, when I put in t equal to 0, gives me cosine 0, which is 1. And on the flip side of things, I've got partial u, partial t is sine x minus sine t, which when I plug in times 0, I get 0. So there you go. I mean, this is the solution to the wave equation for a string which is plucked in the shape of sine at time 0 and let go with fixed endpoints. So there's a specific solution to the wave equation we could play games with under the hyperbolic mapping idea. Yeah? Shall we try? Shall we dare?
Yeah, we
have time. Yes. I have to take trash to the dump today. It's very exciting. And then my mother-in-law and father-in-law are being picked up at the train station tonight. Which is also very exciting. They're fine. We can't argue. So, I mean, I don't speak Cantonese, so. Although my father-in-law does speak English, I think, but not. I think he understands a lot, because he's worked in the restaurant industry a fair amount around people of various, nationalities. But they're both from Guangdong province. They're originally from like a small farming village in mainland China, and then they moved to Hong Kong before Jenny was born. I think Jenny's sister might have been born out of Hong Kong. I forget. So, and then they moved to Brooklyn. So, okay, let's see here. So what was our idea? We take a solution, right? We take a solution over here in the so-called W plane, right? And then we want to move it and kind of see what happens to it back over here at F, right? There's another copy we don't even have name for down here, yet another copy of the hyperbolics. And so ultimately our newfangled solution, I think we called, and so we call this phi, right? And so we said, well, we can construct psi as, how was it? Phi composed with f, right? And that will give us a way to construct a new solution over here based on the solution here's inverse image. So let's see here. So we have, I mean, let's be entirely boring. Let's use the J map. So f of z equal to jz. Kind of one of the stupidest possible hyperbolic transformations. And let's turn this frown upside down. I mean, well, I guess we're probably going to turn it sideways, right? I mean, so if we look at phi of w equal to what? Sine w, the real component of that is this guy, right? This is the real component of the sine of x plus jt. But we're reserving x and y for over here, right? That's our nomenclature. So we're using u and v over here, right? That's our setup. So, but we just want the, we're going to pick off the real part of it. But for now, let's just say sine of what? Sine of w. Am I right? And we know that the real and imaginary components of this are separately wave solutions to the wave equation. And let's see here. We also know that this is the sine of u plus j v, right? Which we worked out is sine u cos v plus j sine u sine v, right? I did that wrong. One of those is cosine. Cosine v, right? No, stink. Plus j, it's my own stupid fault here. So sine, cosine, the cosine absorbs the j, and then cosine of u, sine of jv, but the j pulls out. Right? Are we good? Great. Okay. So if I call this thing S, oh, that's not what I want. What am I even thinking about here? I'm sorry, guys. Well, anyway, I don't need to think about that. I don't really need to think about the boundary conditions at the start. I can just do this and see what kind of boundary conditions, if any, it is subject to and what they look like, right? So what's psi of z? It is phi, right, of jz, which is phi of what? Of y? Oh, I'm sorry, of t, right? Plus what? Plus jx. So I have my u is equal to t, my w, my v is equal to x, right? And so what do we got? We got ourselves a cosine of t. Can't do math. Sadness. Sine. If I could just read my own, sine of t cosine of x plus j cosine of t sine of x. Is that, did I do the calculation? No, I think that if I track back, this point would be what and what? This is pi 0, right? And this is 0, 0. Am I thinking? So how do you get there from, in other words, this is pi, and this is 0. So, that's coming from 0 and 0 pi, right? Also known as pi j. So those 2 points map there and there, and let's see here, if I put, how to think about this. It seems like, it's kind of neat. It's flipped that makes sense though, right? It's flipped our original spatial solution to the imaginary solution. It's just a flip-flopping of time and space, this J map. Interesting. All right. Let's try something a little bit weirder, like z squared, right? Then we don't have this anymore. We have what? We have x squared plus y squared plus 2jxy. In other words, we have u equal to x squared plus, and y is what? T. 2j xt. So u is equal to x squared plus t squared, and my v, quote unquote, is 2xt, right? So what solution to the wave equation does this give us? It gives us the sine of x squared plus t squared, right, times the cosine of 2xt plus j times the cosine of x squared plus t squared times the sine of 2xt. Let's just try to analyze that for a second. If I call this thing u of x comma t, sine of x squared plus t squared times the cosine of 2xt, right? What on earth does that even look like? What kind of wave is that? Apparently it is a solution to the wave equation with unit speed. By construction, that will solve uxx equal to utt. But it's nothing I've ever written down before in the study of such things.